Okay, this is the weekly CSIG call on AI on Thursdays at 10:30 a.m. US Eastern. Today we're very excited to have AI Fairness 360 from Kush Varshney. So I'm handing over to you, Kush, and I am recording.
Okay, great. Thank you, Susan. I'm a researcher at the IBM TJ Watson Research Center, and that's where I'm sitting right now in Yorktown Heights, New York. And I'm in the AI research organization. And what I'll be telling you about is a new open source toolkit that we've released, given the name AI Fairness 360, and the links are on the screen right now. So the first link is an interactive experience. Oops, sorry. The second link is the GitHub repository for the code, and the third is where you can learn about how to do a pip install. Okay. So to talk about the subject, so it's all about fairness, but before getting to fairness, what we need to talk about is decision making. And AI is now used in many high-stakes decision-making applications. I've just kind of illustrated a few here. So that includes credit, loan decisions. It includes employment, so hiring and promotion decisions. The picture, in case you guys are interested, is the building that I'm sitting in, although the picture is from about 50 years earlier. So that is our building. It also includes admission, college admissions, admissions to other educational institutions and so forth. And in the criminal justice sort of setting, it includes prison sentencing and other similar decisions. Okay, so now when AI is being used in helping make those decisions, we should also want there to be trust in those decisions when the machine is making them. And it's not just accuracy that's relevant. So yes, we of course want to get something like 99% accuracy in the decisions, but we also have other considerations beyond accuracy. So one of those is asking, is it fair? Are those decisions fair? Are they easy to understand by us humans? We also want to make sure that they cannot be tampered with. And are they accountable? Can we go back and trace what's been happening? So specifically on fairness, machine learning, which is the basis of all of this stuff in AI, by its very nature is actually always a form of statistical discrimination. And what I mean by that is that the whole name of the game in machine learning is to figure out the patterns by which we can discriminate samples so that new ones that come to us can be labeled appropriately. And if you're figuring out that whiskers helps you differentiate cats from dogs, that's the pattern that you would want to use going forward. But the problem is when you're making decisions, these high stakes decisions about people, that discrimination becomes objectionable when it places certain privileged groups at systematic disadvantage. In particular, there's often, I mean, some privileged groups. That might be white males in the, I guess, young middle-aged white males in the picture that we see on the screen, but it could be different sort of groups depending on what context that you're in. And in many contexts, in the US, for example, due to Civil Rights Act laws from the 60s, this is illegal. And even if it's not illegal in a particular setting, there are lots of social and moral sort of responsibilities for fairness. And when we look at this specifically in the context of machine learning, there are unwanted biases in training data that will actually yield those unwanted biases in the models that are learned from them. And there are actually two distinct reasons why that might be the case. So the first is that there might be prejudice in the labels that we are training from. So often the training data is historical decisions made by humans in the same task. And for either implicit or explicit reasons, these days more often than not it's implicit, there might be biases against certain groups. And that would be reflected in the training data. It would then be learned by the models, and then if these models get rolled out for large-scale decision-making, it would really be scaled very far. And then the second reason could be undersampling or oversampling of samples from different populations. And if that is done, then you can also learn models that are biased against certain groups. Yeah. So now if we move to thinking about an overall machine learning pipeline, so this image is actually from a nice paper by Brian D'Alessandro et al. There's multiple points at which we can think about where bias is coming in and where we might be able to remove those biases. On the training data itself, on the learning procedure, on the output predictions, and so forth. Okay. So this AI Fairness 360 toolkit that we have created, and I'll get to describing in a second, actually has capabilities for all of these points in an overall machine learning pipeline. So the terminology we use, which is slightly different than the D'Alessandro et al. Paper, so we have data set metrics, which test whether a particular training data set has bias or not. We have pre-processing algorithms, which are used to improve that training data to mitigate the bias as much as possible before any learning is done. We have in-processing algorithms, which modify the machine learning algorithm itself, often through extra regularization terms to be discrimination aware. And then there's post-processing algorithms, which don't touch anything until you have predictions coming out. And at that point in time, can modify them to make them more fair. And then in order to check whether a model is fair or not, we also have classifier metrics. And another capability that we've put into the AIF 360 is explainers. So when a particular data set does or does not pass a check for fairness, we want an explanation to go along with it, and similarly for models. And coming to the question of why we even need a toolbox, why can't we just have a few small number of algorithms and metrics that are applicable generally speaking? The reason is that there actually is no one definition of fairness applicable in all contexts. There's many definitions. There was an academic tutorial in February by a professor from Princeton in which he talked about 21 definitions of fairness. We actually have more than 30 implemented in the toolbox. And the reason for that is that there actually is no one definition. Some definitions even conflict. So there's one metric called statistical parity, and there's another one called equality of odds. And except in very special cases, they both cannot be minimized all the way to 0 at the same time. And because of that, we do actually need a comprehensive set of fairness metrics as well as bias mitigation algorithms. And we can't just be happy with one that performs reasonably. And also because of this plethora of metrics and algorithms, we also need to make guidance available to industry practitioners of what to use when and how to think through all of these metrics. And these capabilities are all part of the toolbox that we have. Before finally getting to the toolbox, let me just quickly say why bias mitigation is not easy. And why these algorithms are actually a research challenge. Okay, so if you have a protected attribute, let's say it's race or gender or age or these sort of things, what you can't do is just simply drop the protected attributes from a data set and hope that the algorithm ends up being fair. And the reason is because these protected attributes are usually very correlated with other features that are part of the data set. So as a graphical sort of representation, you see that justice is not blind. So you can actually kind of peek into these protected attributes through the other features that you have available. And then the other picture that's on the screen is an illustration of practice that was used in housing before the civil rights era, and the practice was known as redlining. And what that means is that certain groups were not shown properties in the red sort of areas, and so forth, because the more desirable areas were kind of excluded for certain groups. And this could be done not by saying that it was particularly excluding a group, but it was done based on a geographic basis. So one could claim, oh, I'm using zip code or I'm using these geographical features, whereas you really were actually addressing the protected attributes. So algorithmic fairness is actually one of the hottest topics in the machine learning and AI research community. And it's really exploded in the past year and a half. And there's, I mean, if you were to draw this graph, it's more of a cartoon representation, but it gets the point across, which is what I'm saying. And if you were to have the bar for 2018, it would probably be off the screen. There have also been several industry announcements related to fairness and bias and so forth. So different companies have been talking about the fact that they have tools and that they want to be putting out toolkits and so forth. The only one that we're aware of that actually is out is with biometrics. And they have a very small open source toolkit called Audit AI. All the rest are what, from the best that we can tell, just in the planning phases. So Audit AI in particular is a GitHub repository by biometrics, and what they do is statistical tests for classification and regression, but they do not have any debiasing algorithms, the bias mitigation algorithms, any of the in-processing, post-processing, or pre-processing. There are other toolboxes, all by various academic institutions, that also are keyed in on kind of the fairness aspects. Almost all of them are completely, again, focused just on the testing on the metrics. There are a few that are focused on some debiasing, but don't have as many of the algorithms and options that we have implemented in AIF 360. And so what we kind of wanted to do as we were creating this new toolkit was to really have a comprehensive, which is why we gave it the name 360, toolbox, which has pretty much every fairness metric that is reasonable and has the explanations, has many algorithms implemented already, and kind of has been made extensible such that people can start contributing even more. And this toolbox has only been announced since yesterday, but we already have someone who's put in a pull request with their own algorithm implemented to put into this. So we did 9, but tomorrow when we approve and merge it in, we'll have 10. Okay. So that's a student from the Swiss Federal Institute of Technology in Lausanne. So the other things that we have in here, as I mentioned before, is guidance. Our main objective for this is to provide a way to translate new research from labs such as ours and from all the academic institutions, to translate their new stuff into the practice that various industry folks are using. So we have many industry-specific tutorials already, and we're working on more to do. And just in terms of differentiation, I already mentioned this. This is a comprehensive thing, more comprehensive than anything else that we know of externally. It does have a couple of unique algorithms from us. And it also has some implementations of algorithms that are not available anywhere else. And the reason that we've done it to work for industry in the best possible way, one of the ways we're doing that is because of its architecture. So making it very compatible with the workflows that the practicing data scientists and developers already use. So let me briefly mention the one algorithm from us, from IBM Research, that is in there as a debiasing bias mitigation algorithm. And then I'll, in the remaining 5 minutes or so, or I guess 10 minutes or so that we have, I will kind of go through and show you some of the stuff that we have there. Good. So the algorithm of ours is called optimized preprocessing. This was published in the Neural Information Processing Systems Conference in December of 2017. It is, as its name implies, pre-processing algorithm. And what we try to do is take a data set, a training data set, and work with it in order to make it less fair according to certain metrics for fairness. And it's actually flexible, so you can switch in a few different metrics there. And we have three different objectives and constraints in setting up the problem. The first is a group discrimination sort of constraint. So what that means is we want to make sure that across groups, we have similar performance on the prediction task. And in particular, what we want is the predicted labels to be as independent, statistically independent of the protected attributes as possible. Okay. The second criteria that we include in an overall optimization problem is an individual distortion constraint. So what we don't want to happen is that there be large changes in individual feature values between the given dataset and the preprocessed one. And this is helpful because when you just look at group discrimination, this is everything is looking at it on average. So you can have one big change on a particular sort of data point, but then on average it gets washed out. But that also is not really considered fair because let's say someone was in line to get a very positive outcome, they might just get a negative outcome because of a large change. And then the third issue that we are considering in an overall optimization framework is utility preservation. So what we also don't want to happen is, again, in distribution, we don't want there to be a large change between the given data set and the preprocessed data set that we output. And we do that because we still want to learn the task at hand. Okay. So putting all three things together, we have an overall optimization framework, and it works pretty well from our sort of characterization of it, and it is one of the implemented algorithms. Okay, so let me now switch over to this site, the ai360.mybluemix.net, and show you some of these things in practice. Okay. Oops, sorry. Okay. Okay, so now here is our interactive site. So it kind of gives you a lot of things to think about when you're starting off, and then goes through and tells you about everything that's there. There are the links to the code and the API as well, which I'll show you in a second. So when you're just getting started out, there's an overview which kind of describes what I've already described to you, so we don't need to look at that. We have 3 tutorials already, and we'll keep adding to these. One of them is a credit scoring one, and we actually even have a version of that which I'll show you on the developer works site. We have a guidance document which talks through the choice of these different metrics and so forth. One thing I wanted to highlight here before moving on is that this toolkit is not appropriate for all contexts where fairness is considered. So it should only be used in very limited settings, although those are very often encountered. So there are allocation or risk assessment problems with well-defined protected attributes in which one would like to have some sort of statistical or mathematical notion of sameness. Okay. And we also have a glossary. So all the words that I've been using are captured here. So let me go to the demo. So this is a gentle introduction for folks to understand what the concepts are all about. So we have three data sets here, a German credit scoring data set, an adult census income data set, and a prison recidivism data set. Right, so let me start with the German credit scoring just as an example. Good. And now if I click next, what this will do is call many of the bias metrics that we have, and it will check for these biases. And the protected attribute is sex, the privileged group is male, and the unprivileged group is female, and the task is to predict who gets approved for a loan. Good. So the accuracy is 76% on the classification task itself, on cross-validation, and with these default thresholds, the bias is present in some of these metrics and so forth. Okay. And when we look at a different protected attribute, age, then among old and young, there actually is a lot of bias. Okay. So in 4 out of the 4 metrics that we have, there is quite a bit of bias. Okay. So now, if we go to next here, we can choose to do a few, or I mean, one at a time, but you can go back and try these others. So let me try one of the pre-processing algorithms called reweighing, and let's see what that does. Okay. So once I have done it, I've both removed the bias in the training data and then relearned a data set. And the first thing to notice is the accuracy remained unchanged when I looked at it for sex. The accuracy dropped a very tiny amount from 76 to 73% for the age one. And in particular, if we go down to the age, so there has been a little bit of improvement in many of these fairness metrics, and in particular, if we look at average odds difference, for example, we were below the threshold of fairness, and we're now within the fair range, and we can look at these in detail later on. Okay. So now let me just switch over to this other version of kind of the same demo, but it is with the code so you can see it. And my kind, who is on the call with us, is one of the authors of this. Okay, so this is on the IBM external developer website. Kind of talks through a lot of the things that I've talked about, and then it lets you kind of set up and look at the notebook that is of interest. And now if I go to the actual notebook, we can see that. Right, so this is the actual notebook that we have. All right, so I'm not going to talk through this in detail, but just give you the highlights. So there's the just setting things up. So we have all of the import statements and so forth. So you can see that this is importing everything from our package AIF 360. And then we load the data set, the German credit scoring data set. And then we compute the fairness metrics. So in particular, this difference in mean outcomes is minus 0.12. Minus means it's worse for the unprivileged group. And then we do the debiasing using, actually in this one we use the optimized pre-processing. So that was the NIPS 2017 algorithm that I described earlier. And after we do that optimized pre-processing, we can actually get that fairness metric down to 0. And then, so this is not the fairness metric from above, but this is actually the objective for the optimized pre-processing. So those set of 3 values, so the 2 constraints and the objective, and then here we see the fairness metric, which was 0.12 down to 0.01. So it's down by like a 12th. And the closer this is to zero, the better it is. And really, I mean, this is essentially zero. So the algorithm worked. And so through all of this, we are able to do all of these fairness transformations and so forth. If you want to look at the full GitHub repo, we have everything there. So in particular, all the algorithms, metrics, and explainer classes are here, and so forth. And we also have the API docs. So you can go and look at all of these. So let me just bring up the same on the optimized preprocessing just as an example. And here we have all the parameters of how to call them. And as I mentioned before, it's really done in the scikit-learn sort of format of fit and predict and transform and so forth. Okay. So that concludes the presentation, and yeah, I can take questions now, and we can take some offline as well. So I wasn't following the chat, but Mike, if there's any that we should talk about verbally, we can start with those, or we can just open it up.
Nothing in particular. Let's open it up.
Okay, great.
Yeah, thank you so much, Kush. Most of the conversation has been about the definitions around, you know, bias and how maybe by industry, you know, how can we standardize the definitions a little so that people just don't just do their own thing.
Yeah, so I don't think there is a possibility to standardize because, like I said, I mean, every definition is relevant to kind of what makes sense for that particular application. But if there are certain laws that are in place, so then there might be some standardization possible. So yeah, maybe I can just quickly go through this guidance document. Just at a very high level so that we can understand the choice of metrics a little bit more, okay? So there's individual and group fairness metrics. So what do you care about? Is it seeking similar outcomes for similar individuals? That would be individual fairness, or is it looking at equality across groups? So that lets you decide which sort of metric to look at. And we have some implemented which are actually a combination of both, which are these ones called generalized entropy indices. And they actually capture both at the same time. And then if we are looking at group fairness, which is what most laws, and at least in the US, are concerned with, should we be looking at data metrics or model metrics? So that depends on where in the process that you're looking at things. And then this is the most important, in my opinion. So on the group fairness aspect, so there's two opposing worldviews that one can have. They're given the name "we're all equal" or "what you see is what you get." And with respect to those, what "we're all equal" implies is that you might have some observations, something, for example, being an SAT score, which would be a feature for predicting success in college, but that score is an imperfect representation and it itself might have biases. So what this "we're all equal" sort of worldview says is that we need to do something to make the scores, the features, and everything else more fair by adjusting them. And then the other worldview is "what you see is what you get," and that says that the scores correlate very well with future success, and so we can just appropriately use those scores correctly to compare the ability of applicants. And if you hold that first worldview, we're all equal, then you should be using demographic parity metrics. So we have disparate impact and statistical parity difference implemented in our toolbox. If it's this "what you see is what you get," then equality of odds metrics should be used. So this includes average odds difference and average absolute odds difference in our toolbox. And there's obviously worldviews in between, and these other group fairness metrics that we have implemented are somewhat in between those two worldviews.
That's great. Thank you so much. I didn't know you'd written all that up as well.
Mm-hmm. Yep, so it's available, and yeah, when you're working on a particular application in a particular industry domain, we can definitely go through this and kind of understand things on a more detailed level. Yep.
Great, great. Well, there's lots of thank yous to you, Kush, in the chat. So, and please, anybody else who has thank yous, please go ahead and thank Michael for answering questions and Kush for the fabulous talk. Oh, somebody says, I feel like I need a philosophy course.
Yeah, and that's another point to make, is that we are computer scientists working on this, but we've been talking with philosophers, ethicists, social scientists, legal scholars, and so forth. And it's important because, I mean, this sort of thing, when you hear, the word social construct, that's not a typical phrase that technologists wouldn't use, but we need to be sure that we're understanding all of these things in their full context. So this concept of distributive justice, for example, is one that needs to, truly be understood in the full context of social science and stuff. So that's an important aspect of fairness.
Thank you again. I'll close the call in a moment if there's no one else wants to speak or ask a question. But we're thank you for managing to fit in packed session and in just over 30 minutes. Thank you. Okay. Bye everyone. Maybe I'll see some of you in Bangalore.
Thank you.
Yeah, thanks, Kush, Michael, and Susan. Great stuff. I got a lot of studying to do. It's really good, though.
Yeah, it's fabulous.
Yeah, thank you all. Bye for now.